Okay, so today we're going to cover equations. We're going to cover a wide variety of things, drawing them, derivatives, visualizing, etc., etc.
What session is this?
What's that? Session 2. Okay, so first set of equations we'll be looking at. T squared plus t y is equal to t squared minus t. And for parameters -2 less than or equal to t less than or equal to. So something like this, the easiest way to do it is make a table of values, x, y, t. So -2, -1, 0, 1, 2. You know that from our bounds given up in the top right there. So calculate t at -2. -2 squared is 4, minus 2 is equal to 2. And we'll just go down the line of x's. -1 squared minus -1 squared is 1, minus 1 is 0. 0, 0 is also 0. 1 plus 1 is 2, and 4 plus 2 is 6. For our y values, we will have just the opposite, 6, 2, 0, 0, 1, 2. Okay, so we got our values and we can just make our plot, x, y, negative, so we'll have 1, 2, and 1, 2, 3, 4, 5, 6. We will have 0 and 2. We will have 0 and 0. We will have 2 and 0. And we will have 6, 1, 2, 3, 4, 5, 6, and positive 2. So the way this plot's shaping up, it's going to end up something along these lines here. Didn't really draw it to scale, but you can see it's sort of a parabola that's facing the wrong way. Mm-hmm. And you can tell which way your t's are proceeding just looking at negatives to positives. Since the negatives start up here and come around, we know that it's proceeding in this direction. So I suppose this arrow isn't technically correct, but that's what we got. Okay, so that's just a simple method for plotting your parametrics. Even with your more complicated parametric equations, it's a very standard format for finding a graph. Okay, so now we're going to do just a quick elimination of parameters, and that's essentially we have a function of x in terms of t, and a function in y in terms of t, and we want a function that we're familiar with. So in terms of like x and y, which means we're just going to solve for, say, t in terms of x, and then plug it into the y equation. So over here, if we solve for t, we'll have 4t equal 3 minus x. T is equal to 3 minus x over 4. Take that, plug it into our y equation, and we get 2 minus 3 times 3 minus x over 4, which is y is equal to 2 minus 9/4 minus 3x over 4. And I suppose I could simplify this. That's 4/4. That's 8/4 minus 9/4 is a -1/4 minus 3x over 4. So that's our y in terms of x based on the parametrics we were given. standard function that we know how to graph. All right, so that's another method that we can use to solve for these types of problems. Okay, so let's go with another elimination of parameters with something a little bit more interesting. Let's try e to the t minus 1. And y is equal to e to the 2t. Okay, so this time around, just solve for x again. So, let's see here.
So that e to the t, not the plus, right?
What, up here?
Both, yeah. T.
Yeah, these are both e to the t and e to the 2t. No pluses or anything like that.
Okay.
Because we don't have any other terms. So a plus wouldn't really make a whole lot of sense.
Sorry, I got chemistry on that.
No, that's no problem. All right, so this time I guess we'll solve for y. That's a little more straightforward than trying to figure out x. So in this situation, it's pretty easy to just take the ln of both sides. Ln of the absolute value of y is equal to the ln of e to 2t, absolute value. Simplify our ln, can bring the exponent out front, 2t, ln of e. ln of e is just 1, so the ln of y is equal to 2t. And then we can divide the 2 over, so t will be equal to, and we can either have ln of y over 2, or we can bring the root in for simplification. So we'll go with that, ln of the square root of y. Okay, so now we just plug that back in over on the x side. So x will be equal to e to the ln of the square root of y minus 1. E to the ln of anything is just whatever's in the ln, so x is equal to the square root of y minus 1. Yeah. And then add the 1 over, square root of y, square both sides. And we have y is equal to x squared plus 2x plus 1. Again, just a straightforward x squared, some kind of parabola. We know how to plot these sorts of things. So now we have this in terms of things that make sense to us. And you can see the whole point of working with these parametrics is really just to break them down into terms that we understand. I'd like to just evaluate a derivative of two parametric equations now. So x equal to t minus 1, y equal to t to the third plus 1. And I want to find dy dx and the second derivative d squared y over dx squared. So when we evaluate dy dx, we take dy in terms of dt and divide it by dx in terms of dt. dt's will cancel and we'll get dy dx. So first we'll take the derivative y with respect to t is going to be 3t squared, and we divide by the derivative of x with respect to t, which is just 1. So it's 3. The second derivative is going to be the derivative with respect to t of dy dx, we found on the last one, divided by dx dt. That's just a formula. There's a proof for it, but we're not really concerned with that. So we take the derivative of the first derivative we found before. Derivative of 3t squared is just going to be 6t. And divide by the dx dt we found the first time around, which lucky for us is just 1. So our second derivative, 16. And that's how you find first derivative, second derivative, change in slope and concavity for these things. Just a simple process, follow it, and it'll work every time. I think now we'll try something a little bit weirder. I'm going to find dy dt dx dt again, but no, there we go. This time we're going to bring trig functions into the mix. Yay! Okay. So dy dx. Again, dy dt over dx dt. Derivative of y with respect to, well, I guess this time around we're in terms of theta. Dx of theta. Okay. So we have the derivative of y with respect to t, derivative of secant theta is just going to be secant theta, tangent theta. And we are dividing by the derivative of tangent squared theta. So chain rule it, 2 tangent theta out, and then take the chain rule, derivative of tangent is secant squared theta. Tangent cancels, one of the secants in the denominator cancels. Secant is equal to 1 over cosine, so in this case it's going to be cosine of theta over 2. Simplest form of what we've got here. And then, excuse me, d squared y over dx squared d theta dy dx over dx theta. So derivative of cosine over 2 is just negative sine theta over 2. And we divide that by what we found last time around, 2 tangent theta secant squared theta. Yes, okay. So, let's see here, I'm not seeing a whole lot of cancellation here, but 2's are going to multiply to give us 1/4 out in front. Tangent is sine over cosine. So the sines will cancel out. We'll have a cosine in the numerator, and that's 1 over cosine squared. So it should come out to cosine cubed theta. And I believe that will do it for it. Yes, okay. That's our answer for the second derivative. Just more proof that if you follow the process, these things are relatively straightforward. Okay, so I think that'll do it for our examples today. Hope that all made sense.
Yep.
If anything didn't, feel free to ask, and the floor is now open for general questions.
I have a question on the last